Honorary Senator of Karlsruhe Institute of Technology, Professor Thomas Hirth, dear Mrs. Susanne Schroff, President of Schroff Foundations, Professor Manfred Kappes, Distinguished Professor, Karlsruhe Institute of Technology, members of the Board of Karlsruhe Institute of Technology, distinguished professors, colleagues, ladies and gentlemen. I'm honored to receive this International Excellence Award of KIT and Fellowship of the Schroff Foundation. Let me thank KIT, the jury, and the Schroff Foundations for this very special and important recognition. I'm glad to be the first in the series of awardees who will enrich the KIT system in the years to come.
1 second.
I chose to talk about molecular acorns, which have excited me over the years, and research that has taken me to build institutional oaks. So over many years of work, I have come to realize that the most essential problem that the planet faces is water. This was a picture taken by the Voyager 1 as it just passed Uranus, some 6 billion kilometers away from planet Earth on that day, February 14th, 1990. So the picture that you see, of course, Voyager is still continuing its journey some 23 billion kilometers away. So as it passed Uranus, and it looked back and took a picture of the solar system. And there, in that part of the sky, there is this blue dot. The blue is water, and the dot is our Earth. As you know, therefore, in this planet, water is the most important inheritance of the planet. Although I did not know about this, I lived in a region which is full of water. As Mrs. Susanne Schroff talked about, that region, there are 55 rivers. So I lived with water. But this water is so beautiful, this place is, but all these rivers in our country are contaminated today. So we monitor one of these rivers. But I don't want to get into that story, but to tell you that the solution for that story is materials. So what is that solution? Well, you know, in 1865, when this novel was written, Jules Verne wrote that novel. It talked about sending a man to moon with a rocket. The rocket, of course, had to be made with the most advanced, high-strength, but low-weight material. And Jules Verne talked about aluminum. Aluminum at that time had been discovered, but it had not been, in commercial production, which started only in 1878. And that is a story of making a rocket of 900 pounds of aluminum and sending that to moon. Of course, it didn't go to moon, it became a satellite, and that is that story about. What I wanted to tell you was that if you want to find solutions for a larger challenge, of course, materials is the way forward. That kind of materials research over quite some time took me to atomically precise clusters, as Manfred talked about. So in the first portion of this lecture of molecular acorns, I will be talking about this. That today we have clusters that can be made in the laboratory in reaction vessels atomically precise particles, an Avogadro number of these particles at room temperature or near about room temperature. And you can characterize with advanced tools, with mass spectrometry, with, with so much of precision. 7390.5718. So this is how you can measure mass spectra today with advanced tools. You can crystallize them, you have crystal structures of them, and we call them as gold 25 or silver 25 or silver 29 kind of molecules. But there are a whole lot of other molecules that we work with. And we build them in the laboratory, and we build materials, assemble solids with that. And one day we believe that the world can be built with molecularly precise materials. And that area of science is advancing. So as Manfred was talking about, one day I was looking at, to give you a feel of what kind of science that I do. One day I was looking at the solutions of these clusters. And they, at room temperature, if you irradiate with ultraviolet light, they are luminescent, giving you some red luminescence. Some of them, not all of them. And in visible light, they look like this. Now, I was asking this question that they're all molecules, and molecules should do molecular reactivity. Can I see these guys reacting in solution? And by the way, I'm talking about reactions of these clusters, beautiful clusters, in solution, just like benzene and toluene and things like that would react. How about looking at that? And these are not reactions that happen on the clusters. We call them as catalysis. So these are reactions wherein these clusters participate. And we wanted to do that with techniques such as mass spectrometry. Well, one experiment, if you want to do experiments of this kind, chemists would like to call these as molecular reactions. The moment you say molecular reactions, you write a formula, something like a reaction scheme starting with this formula, this formula. This formula would correspond to that particular molecule. This would correspond to that molecule. They react. They react meaning, right from Lavoisier, we know about chemical reactions, and they must follow certain kind of conditions, and there should be mass balance, there should be thermodynamics, there should be kinetics associated with it. Can I study all of these with nanoparticles? So that was the excitement, and we wrote that paper sometime in 2016. So to give you a feel of this, so if I take a molecule such as this is a chemical symbol for something like this, an acronym for this. And I have another cluster which also is protected by this very same entity. The acronym is fluorothiophene. That's a reaction. And I thought, why not this be observed in solution? And the tool for that was soft ionization mass spectrometry. So if I take pure cluster of this kind, I'll get a peak like that, and this cluster will decompose or fragment in the gas phase to give you some peak like this. So these are the only two peaks that you would have if you take just pure this cluster. The moment you add this, of course, this will ionize and give you some peak which will be beyond this mass range. But then I started seeing something here. Suddenly a peak 1 comes up, peak 2 comes up, etc. And here also some peaks come up. And these are nothing but exchanging one Au atom with an Ag atom, keeping the nuclearity the same, essentially 25 atom cluster. Now, this a little later, after 1 minute, these peaks go up in intensity. That peak will come down in intensity. Later on, this will be completely gone. Another kind of composition will emerge. So I am doing molecular reactions of nanoparticles with atomic precision. So I can do this experiment with that cluster and that cluster, again protected with ligands, and we saw that a cluster of that kind is reacting with a cluster of this kind. Here I label this cluster as 0, 25 to indicate that there is no silver in it, to indicate that there is no gold in it. I write it as 25, 0. This is what I have to begin with. The moment I mix, suddenly some new peaks come up for the reasons I told you. And these, if I expand it, I see many peaks like that. They are all atom exchanges, but there is a peak here which is of greater intensity. Today we understand that this is because of greater entropic contribution to the total free energy of the system. Okay, so how do they react? And well, if a cluster, another cluster were to react, just like molecules, they should come together and form a transition state of some kind. And can I have a transition state? So in the initial stage of this reaction, if I expand this region, I get a peak here, which is nothing but two clusters coming together and forming a dimer, a heterodimer, so to say. This is one charge state, 1 minus, this is 1 minus. They come together and form a 2 minus charge species. And we study this and all that. And these cluster from that become many other reaction products in the course of time. Well, you can compute it. And you say that these clusters come together at interatomic distances or something, or intercluster distances are things like this, 2.9 angstrom or 3 angstrom, where atom exchange is feasible. So I have, to begin with, I start with a silver 25 and add a little bit of gold 25, I get atom exchange. Little more gold 25 here, some more atom exchange to this equilibrium mixture. I exchange all the atoms, and I can go all the way to gold 25 by changing one atom at a time. This is not to say that silver is becoming gold. This is not alchemy, or this is not things of that kind. This is reaction chemistry. Many other species get formed, but this is something that happens. So later on, Manfred, with a lot of effort, found that it is not just that this particular dimer gets formed. There are many, many dimers in solution. There are so many clusters in solution, and they all form dimers, and so many peaks come up in between. And with a kind of modeling, they understand how reactions evolve. Oh, this is a complex soup of things that we have created. And here we looked at silver 25 decreases in solution, but this cluster comes up, one atom exchange comes up and decreases again. It becomes 2 atom exchange, increases and decreases, 3 atom, 4 atom, 5 atom. And then you do what is called consecutive chemical reactions. Very interesting physical chemistry across the world. You study consecutive reactions. And you see consecutive reactions come about in nanoparticle systems. Oh, such a fascinating subject. Well, with Papri, I was asking this question, Papri in the audience here, I was asking this question, atoms are exchanging if A and B are reacting. But you know, this atom cluster A is moving around in solution, and it is encountering another cluster in solution. During that hitting, will they exchange atoms? This is like water. You have water molecule, and it hits another water molecule. Hydrogen or protons exchange. And this is what we see when H2O is added to D2O. In just less than a second, you see HDO in solution. Do you have these kinds of things? So to study this, Papri made this cluster, silver 25 with 107 isotope of silver. silver 29 with 109 isotope of silver. That's two separate compounds in the laboratory, in bottles. But you mix these two together. In the first mass spectrum, in just under a few, let us say a minute or something, or 2 minutes, you start seeing this, nothing here, nothing here. Atoms have exchanged. So you start seeing a completely new kind of science. This is very difficult for a materials chemist to understand, that a piece of metal, another piece of metal there, they're seeing each other, boom, atoms change. Now, we don't fully understand all these, as Manfred was talking about, but there is a whole lot to do. We build materials with this. So I'm not going to take you through that story of how material science evolved at atomically precise materials length scale. So as we understand that these are very reactive, of course this kind of science of reactivity we knew earlier. So when I was working on these molecular kind of materials in around 2002, in our country, we found that pesticides are there in water at a very large concentration. And I was asking this question, should I find or can I find a solution for that using our materials? We found, let me just go back, we found that we can have nanoparticles of metals reacting with pesticides, which are oftentimes halocarbons, do dehalogenation chemistry, remove these pesticides at room temperature below the detectable levels that you have in solution. We built the first company in this, or product in this area. That was my first patent, and that patent was in 2005. The product got introduced in 2007. Well, so since then we have been working on, and we found that for materials to work in water, the first and foremost realization is that they have to be affordable. They have to be sustainable. And people, whatever be your solution, if it is not affordable, no technology is going to reach people. So I said, what should be that affordable cost? I said 5 paisa per liter of water. That is my limit. 5 paisa, Madam Suzanne would know what that means. 5 paisa is nothing. But it has to be not at that kind of cost. Only then it is going to be affordable. Today, I tell you, we are supplying water at 2.7 paisa per liter at a 1 million liter scale plants. So, what is the basis of this? The basis of this are nanomaterials, which are nanoparticle assembled composite materials, and they clean water as they pass through these materials. So in the process, you can also remove contaminants. So this is another material which was published in this place. So you have composite materials, as Manfred was talking about, iron-based, iron oxyhydroxide. These are metastable iron oxyhydroxide, which normally cannot be stabilized. But you stabilize that in the nanoparticle form in a composite, and that material, because of its specific sites available, they remove contaminants like arsenic from water at that concentration, 200 parts per billion to less than 2 parts per billion at a very high rate, and today we can implement these. So we can put this in places like West Bengal, and you can then put this in schools, and this unit supplies 1,000 liters of water every day. It can run for 1.5 years without changing these materials. But it can also go in this kind of scale. And today it can go, well, people have written about it, and we can do this at that scale. So here is a village which is having about 2,500 people, and there is this water supply system government has introduced. Let us say you find arsenic in it, beyond the levels tolerated. And you can come up with a filter using those materials I told you, supplying something like 200,000 liters of water a day or 1 million liters of water a day, depending upon the population, at a cost of 2.8 paisa per liter. So this has been now nationally approved as a technology. So anywhere you see this, people can implement it with governmental support. And that way, one state has become arsenic free. In the course of this implementation, we found that there are other things in water, such as uranium. And we modify these materials. And today, the first uranium purifiers have been implemented. So that way, we have 1,700 community installations across the country and supplying water. Lots of other technologies, as Manfred was talking about, have come out of the group. And you need to also monitor water. With advanced materials, you can develop sensors, and this data that is being monitored on the pipeline, they go across, and of course, people across the world also do this kind of things. To show you an example of how cluster science is helping here. These clusters are luminescent. You can incorporate these clusters in membranes, and they are luminescent, and these can be made with things like nanofibers. And these fibers are impregnated with clusters, and they are very sensitive. For example, this is just with 8 ions of mercury. 8 ions of mercury, the luminescence goes off, and it is very selective. And today, these clusters are not that stable. So our puzzle, of course, our real hard work is, how do you make these materials really stable at reasonably high temperatures? So Arijit in this audience, who is now with Stephanie, is having this cluster that he has made, 21 atom cluster. And this is large crystals. And what is more important is that they are stable up to 300 degrees. 300 degrees centigrade. So those materials, some years ago, we thought that atomically precise materials are only good in your laboratories. They are going to be important in the field. And how can they be useful? Of course, you can't make 2.7 paisa per liter drinking water solutions with those materials because they are expensive, but they can be useful in detection. So lots of detectors we work with. For example, today, this is not my work, but detectors as small as this these are spectrometers. Spectrometers. Meaning you can put this guy on a mobile phone and measure a spectrum. In 2 years' time, I'm told by this company that the size of this is going to shrink to 2.4 millimeters. And with that, with the analytics, with the data over the cloud, it is possible to measure a Google map of water quality. And we think that it is possible to be done with atomically precise clusters. So here is a cluster in the laboratory that we make, similar to what Stephanie makes here. And these clusters can be electrosprayed by a technique called soft ionization methodology and onto water surfaces, creating micron scale platelets. And they are extremely sensitive. As you see, they are sensitive to arsenic. And real from tap water, without any purification, put a drop of it, and you can measure arsenic down to 3.7 ppb. And so selective that no other ion gets detected. So what do? You develop an electrochemical device as small as your mobile phone, put it in your pocket, and put a small stick here, like the device that you have or the sensor that you have for measuring your sugar, glucose in your blood. And the data comes on the mobile. And I don't have a device to show you, but this is what we make in the laboratory. And what it means is that across the world, at a cost less than 10 paisa, you can measure arsenic. with devices that are in your pocket. Of course, the electrochemical potentiostat will cost a little bit of money. That's an Indian cost. It is about $80. And it is possible to have that device with one measurement less than 10 paisa. It is possible to map water quality. Today we measure water quality across the country. Not with that device, but with other devices. Right from there to here, this is 3,000 kilometers. So we measure water quality, and many, many qualities, as you can see, can be done. In this process, we have learned a lot of things. But for us to become a water secure world, we need everyone else also to innovate in the area of water. So we have built the International Center for Water for anyone to come with an idea in the context of water and build a company and build a product in the field. This kind of a technique or this kind of an activity is first of its kind. To tell you, there are many other things that I do in the context of water. This is ice that I grow on surfaces, which are lattice matched, we say. We create such ice surfaces. We study this in the laboratory. We create new materials of surface science. To study that, we build new microscopy. And this is our new microscopy building with a cryo-electron facility so that we can examine materials of this kind like cubic ice. And we also build companies across. The IIT Madras Research Park is a place where companies are born. And all of these become possible with international cooperation. People of the kind that you are hosting me here. I have published papers with all of these people. Of course, more people are welcome to join that large initiative with young people. Some of them are here. And an effort of this kind is possible only with governments, as non-governmental agencies, working with the system, right from students all the way to people on the ground. Have a large number of movies which will tell you what this kind of science has done to people and what kind of impact it has made. It has been possible with this great institution, IIT Madras. Thank you very much.